Welcome to Physics Office Hours. My name is Eric. In this video, we're taking a look at my live stream that happened on June 24th, 2020. We'll be going over special relativity. What is space-time? What is a point in space? And how do we utilize that mathematically? If you like physics, if you have any questions about this stream, this particular video, or about physics in general, feel free to stop by. I stream every Monday, Wednesday, and Friday from 3 p.m. Eastern to 6 p.m. Eastern. For any updates on the stream, feel free to follow any of my socials that are listed down below. If you like this content, I'm relatively new to making physics content, but feel free to subscribe. I'll be putting out a lot more in the near future, and hopefully you find something that you like. As always, I'm open to comments and suggestions. Feel free to leave a comment below and let me know what you'd like to see, both content-wise or what you'd like to see with the stream. As always, thank you, and let's roll the intro. It's physics time! Let's do it! So, if I were to ask you, what is a point? I still get angry at clouds like Grandpa Simpson. That's too bad. That's kind of funny though. Do I have that picture? I should have that picture. I might need to make a new scene for it. Let's see, let me get that picture up. So when you guys are thinking of your answers, what is a point? A point in space. Space-time, more particularly. What do we got? An event. Nice. Exvention. He's been here. He relativities. Defined as R when R is equal to X, Y, and Z and T. Give me more than that, Jax. I mean, an event is pretty much the right answer, but I'm kind of curious to have you elaborate on that. What is an event? What is a point is an event. I'm in Python mode here. Well, Python's not reality. Despite your professor who tells you need it to understand reality, Python's not reality. Let's see, a location at a specific time under a certain choice of coordinates. So is location an event? Is location another way to say event? Thanks for the detour, but yes to the equations and beyond. Awesome. I'm glad we have these conversations, Novo. It's very good. It's very, very good. Special relativity. What is a point in space made up of fundamentally? And I think that's something we don't really understand. Like, anything could be points, right? I guess an event is defined as coordinates X, Y, Z, and T. I don't know. I think it's a little bit more than that, right? I think an event is, you know, the coordinates, right? But it's also what happens at those coordinates. Which is why I think we get the wrong idea when we start thinking about space as something that's like this background, this untouchable thing that we have that we can't mess with, right? When in reality, the only way we really understand it is what happens at that point. That's an event. So, yeah, so I would say that probably the best way to think about it is each point in space is not an object, but instead it's an event. And an event is a classification of something that happens, okay? Why does that matter? Well, because then we can start talking about what happens between 2 points in space. Between 2 points in space, we could talk about 2 events, right? So for instance, if this is you're here. This is almost as good as the Wile E. Coyote that I just erased, right? If this is you and you're wearing a top hat, and you have a flashlight, or a laser pointer, or a flashlight, whatever you want to say, and it's going to give off some beam of light to your friend who's over here. Also wearing a top hat. You guys are top hat buddies. But they don't have a laser, they have a detector. That happens to look like a target. Right? So you're gonna shoot, we're gonna do a lot of colors today, I think. 2 events. We have event A, and we have event B. Right? We don't necessarily talk about the points as coordinates. Why? Coordinates are arbitrary. There's an oh man, I was literally about to say those words. There are elements of a set called a manifold. If that manifold is metric space, then you have distances defined between those elements. You can make up coordinates charts, and the charts, the associated maps, and elements, and the event, and the chart. Very good. I am 1.5K points away from pony. Well, I'll include some free ponies this time around, just for fun. I'm not gonna make you guys spend your well-earned channel points. So, if we have, all right, the coordinates are arbitrary. Who cares, right? We don't care about coordinates. Coordinates can be whatever. Well, we care about what's happening at these points, right? At these points, we can talk about light passing here. We talk about light going from here to here. At this event, there's light. At this event, there's light. That's what matters. That's how we talk about reality. That's how we talk about space-time. That's how we talk about the interesting, we do the math of these things, right? When we have these events, now we can talk about things that we can measure, like distance. We can measure time, how long things take. We can start measuring change. Now we have something meaningful, right, in mathematics. We have a distance in space, a distance in time, we have distance. Why does this mean anything to it? Why does it mean anything to us? This means something to us because we can talk about how change happens. This is the whole point of physics, is to talk about how things are changing. And when we talk about this change, then we can talk about predictability. And when I say that physics is the understanding of the mathematical world, the mathematical understanding of the physical world, then I say it is for this, right? We need to mathematically understand change, because change is the only thing we know. Which is one of the reasons why these coordinate systems and everything are so arbitrary. Okay, so we can talk about the distances between Alice and Bob in both space and time, but the whole idea of what we call those points, it doesn't really matter. Like Exvention said, the coordinate system is arbitrary. What matters is the distance and how it changes and how we manipulate it, right? So with that, we can start to see where these light cones and these diagrams, the Minkowski diagrams and things like that, come from. Right? We have some point in space. Going back to A. Okay? And you can imagine that, off in some far distant future, or past, that there was a bunch of stars. Right? And each star would give off light. And the light would radiate away from the star, but you can imagine a couple of those light beams, a bunch of them, I should say, coming directly to this point A, where you are. And you're collecting the light because you're happy in your telescope, which, looks like this. And it's a beautiful thing, right? And this event A is the spot where you are standing outside in your backyard and you're collecting all of the light, and then say, it's, you are at a certain coordinate system, x1, y, x1, y1, and z1. It's 9 p.m. at night, t1, and you've collected a bunch of star data, okay? Each of these stars that have hit you came from x, 2, y2, z2, t2, x3, y3, z3, t3. You get the picture. Like, there's events here let's see, 2, 3, 4. There's events that happen here, 1, 2, 3, 4, or we'll call this one 1, you know, where you can establish coordinates, and then you can start talking about distances, about times, about everything. But the event A is when all of these things converge. You have the whole of reality, the whole of everything that has been and is to, you know, not is to be, has been in the past, all converging from the distant light cone into the one single spot, and we call that an event. Okay? So these are events. That is how you are to see space-time. So what's another way we can talk about it? Well, let's get into a little bit of the math. I'm not going to go super heavy with the math, but let's say that if we wanted to say there's a general way to write distance, and I'm talking about distance in space-time, not distance in just space. Talk about distance in space-time. We can say that that's going to be delta s squared. Well, delta s is the distance, and then yeah, let's leave it as delta s then. Okay? We can say something about this. This is one of the beautiful things that Einstein did. We can say that this delta s is going to be equal to negative c times delta t squared plus delta x squared. And we're only going to do in one dimension, okay? We're not going to worry about, there's, you know, plus, we could say plus y squared plus e squared. But just like we could add those, we can set them both equal to 0 and say that there's no change in the x or y, and we're only interested in the change in x. Okay, just to simplify things. Right? So now we have this little equation here to handle. It's nothing, it's the change in s, which is the general change in direction, is given by the speed of light times the change in t. Don't worry, we're going to set that equal to 1 soon. Speed of light times the change in t, plus delta x, the change in x. Okay? This is it. This is as far as the equations are going to go. Can we do something with this? So let's do this, right? If we were to have a triangle in x and y space. So we're going to have 3, 4. What's the side of the hypotenuse? Somebody say. The size of the hypotenuse. If this is 3 and this is 4, what's the size of the hypotenuse? I am worried you will actually set up c equals 1. Oh, I 100% plan to set c equal to 1. That's going to happen very soon. Tyrion's right, it's 5. Whoa, it's almost as if like s equals 0 gives you dx dt. Not yet, expansion. That's the fun part. You're ruining it. We will do that. But don't spoil it for the others. All right. So yeah, so it's 3, 4, 5, right? We know the Pythagorean theorem, a squared plus b squared is equal to c squared when we're talking about the sides of a right triangle. So if we have a squared here, b squared, c squared. A squared plus b squared equals c squared. We did it. Okay, that's all well and good. So now, this is in Cartesian coordinates. But what if we talked about space-time? Okay, so now this one's going to be a little bit more complicated. So I have another picture I'm going to bring up. I still have no idea what's going on, but seeing cat time cat seems elegant to me. These are delta. It's a delta. It's c delta t. It just means the speed of light times the change in t. Okay? You don't really need to know what everything means. Just know that this is the change in t. Like I said, I'm going to set c equal to 1 soon enough. These are different c's, by the way. This is the speed of light. This is just a c, a distance. And so we know the Pythagorean theorem. We can work with it. We can deal with it. It's fine. This is Minkowski space. It's just a name. Don't get terrified. What does Minkowski space mean? Well, that means that if we transform space, that this ds is always going to be the same. So if we have a different one, if we do a Lorentz transformation, like say we're now talking about something in motion, okay? So for the sake of argument, we know if something's in motion, then the change in time is going to be different in a different frame. The change in x is going to be different in a different frame. We know all this stuff. Length and time both get contracted. So we could rewrite the same thing in the following way. If it's under some velocity, then we could say that delta s squared is still going to equal, if it's a Lorentz transformation, delta t prime squared plus delta x squared, x prime squared. That's the point of what this is. This is a general thing to say no matter what the speed is, the distance is going to be the same. Okay? All right. And you can just sort of see how it's going to change. So then, like, you can do a transformation to say, like, well, what does x see? You know, what does someone see in x prime? You can do the transformation between the two different frames. And we're not going to get into that math. But if those of you who are interested, you can see the translation from like what's the distance? You know, what does x look like in terms of, you know, blah 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 x prime? And you can just, it's going to be like the Lorentz factor and whatnot. But we're not going to get into that because I told Bit I wouldn't. All right. And I want this to be about other things too. So anyways, we know how to do the Pythagorean theorem. We know what it stands for. We know what it means. But what does it mean if we talk about it in Minkowski space? Or if we just try to do some of this stuff in Minkowski space? Well, let's take a look, okay? Let me bring it up here. I gotta make a new source though, I think. So bear with me for a second. Oh, look at that. Picked it right away. S is just a distance. Now show the relativistic Lagrangian is invariant under the transformations in SO31. So can you guys see that? Just that little picture there? It's a picture that I drew and then took a picture of. It's not a constellation. But I assume you can see it then. Alright, so now this is Minkowski space, and we're going to get into what a light cone actually is. But again, let's just think of it as, instead of x and y now, we have some ds that is equal to a new graph, and we're going to call that t and x, okay, or ct more specifically, and x. Soon we're going to set c equal to 1. You wait, it's coming. But if you look at that picture, you can kind of see like where the axes are. That we'll just call this bottom, like the bottom corner, the denominator, or the, where is it? We'll call this bottom corner over there the origin, moving out to some distance x. And then this is, then we're gonna, our y-axis, where is it? There we go. Our y-axis is gonna be c and t. But again, we're in Minkowski space, so things are gonna look a little different. Well, let's do some calculations. Very baseline calculation stuff. So now let's take a look at a few of the lines. So see, you can have some, these things are like just to represent two different frames of reference. You have events A, B, and C, and you also have events A prime, B prime, and C prime. So now let's talk about the distances between all of those events, right? And how are we going to do that? Well, we'll talk about the length like this. So we have A and B. That's one length. What's the length of A and B? Well, the length in delta t is going to be 0 because it's not changing in time at all. But delta x is changing by a factor of 5. So that's easy. We can say delta s squared. If you want to see the whole thing, you say delta s squared is equal to negative c times delta t squared plus delta x squared. Okay, so what's delta s equal to? Delta s is equal to, well, we should say that AB is actually delta x. Delta s, excuse me. So what's delta s equal to? Well, this is 0 plus 5 squared. So delta s is just equal to 5. So what's AB? Well, AB is equal to 5. Very straightforward. Okay? What's next? Well, what's BC? BC is now a change in, there's no change in x. There's no change, or I'm sorry, yeah, there's no change in x, but there is a change in t. So we just perform the same thing. This is where we do it. Let c equals 1. It happened. It finally happened. I hope you guys are excited about it, as I am. Let c equals 1, and BC is equal to 3. Now, boo! Why is c equal to 1? Well, we call this natural units. Now, everything's in terms of energy. And it doesn't really matter what units we have right now, because we're not talking about that type of stuff. So, units, I know everybody tells you that units matter. They don't matter that much when you get to this level, okay? They still change the equations and whatnot, but it doesn't do any harm, okay? So we're going to use c equals to 1. And what do we get? Well, AC is equal to delta S, which is going to be the square root of negative delta t squared, so that's 3 squared, so that's 9, plus delta x squared, so that's 5 squared, so that's 25. And this is equal to the square root of 16, which is 4. So this is the first Dr. Young thinking he's all smart. And then it's just a simple, hey chat. But if we look at the last triangle again, when this was y and this was x, and we had 3 and 4, and we had 3, 4, 5, where the hypotenuse is 5. Now look at the triangle in Minkowski space. The triangle in Minkowski space is A to B is 5, B to C is 3, and the hypotenuse is 4. CT X looks like this. 5, 3, 4. Weird. So, notice the difference between the two spaces, right? We have a 3, 4, 5 triangle that everyone knows about, is very comfortable with, but in Minkowski space, now we have a 3, 5, 4 triangle? It's just a weird way to think about these things, but this is the way we have to do it. So now take a look at the next one, right? This is going to be even stranger. Look at the triangle, or the triangle to the right. The A prime, B prime, C prime triangle. Where's my eraser? C is still equal to 1. If I ever write a C, it's an accident. It's supposed to be 1. Now let's do the same thing. What's the length A prime, B prime? Well, that's going to be equal to the square root of negative 3 squared plus 3 squared. That's 0. Now we have something that we've drawn. What the crap is a Minkowski space? It's just a space. I said don't worry about it. Don't worry about what Minkowski space is. Minkowski space is the space where this happens, where we have a triangle, A prime, B prime, C prime. Look at this. I'm drawing a triangle. Oh, that's not the triangle. This is why I drew a picture ahead of time. I took a picture because I know better. Here we have C prime, B prime, and A prime. We have something here. What's the distance? We just measured the distance. It's 0. It's 0. That's weird. Where are all the cats? Let's do another one. Let's do B prime to C prime. I mean, I hate to be a spoiler, but it's 0. Same thing, right? Last one's A prime, C prime, and there's no change in delta x, there's only a change in delta t, so we get 6. You can count it if you want. It's what Eric calls his garage. Thank you so much for the follow, Snark. Welcome. Welcome, welcome, welcome. Oh, I put this in front of my alerts. What a bad guy I am. There we go. Bad guy. Anyways, welcome, Eric. Thank you for following. All right. If you have a question, just ask it at any point, and I'll get to it when we're done with this. We are going to watch a short video after this. It's like 10 minutes long. PBS Spacetime is very interesting, very good. We're going to learn what to do with all this. So now we have these different events, right? I called these events. And we have to kind of figure out why this distance right here is 0. That doesn't make sense intuitively. But it does if you know what a light cone is. What's going on? Come on, man. There we go. I like how you joined the queue to ask me what's going on. Okay, so let's talk about light cones, and then maybe this will start to all make sense. We have this different space where, like, if we were to draw, if we were to draw some sort of triangle in it, we can actually have a triangle that has sides that are length 0. And that means something. That makes sense. So what is this? So let's take one of these points. Let's take 8 prime. Okay? And we're going to draw... Oh, I got colors, dude. I got colors, dude. Look at all these colors. We're going to call it... We're going to do purple. We're going to make this pretty, and it's going to stay up for the rest of the day. A prime. Now, A prime is going to live on the axis that we just talked about, right? We're going to say that there's some CT, some X. Okay, so now we have our two axes that we talked about. This is Minkowski space, where you have CT as your Y and X as your X. And this is where we go... Stop using colors. Oh no, are you gonna copyright strike me, Dr. Young, for using colors? Look, I just got excited because I found a new box of colored chalk, okay? Don't nobody take this away from me, please. Please, please, please. Okay. Now, we're gonna go back, and this time we're gonna draw our stars again, okay? And they're going to have starlight that's coming through to A, to our event, okay? Now let's draw the big boy. The light cone itself will be in white, okay? And what does all this mean? Well, this line, when C is equal to 1... Oh, I drew a C. I told you I wouldn't. Let's do this. C is equal to 1. Okay. Take care of that. This line right here is delta T over delta X. Right? What does that mean? That is when delta T over delta X is equal to C. Sorry, that's what I meant to say. What does that mean? Well, delta C, remember, C is equal to 1. So what does this all mean? So we have our x-axis, we have our t-axis, our time axis, we have an event, and everything that happens in this past light cone will have some line that will come and intersect at this event. You can think of an event happening at every second of your life. What up, Drop Bear Antics? How are you? Good to see ya. And at every event, you can think of all the past things happening, every past event happening within the light cone, and then some information will travel inside the light cone. That's very important that it's inside the light cone, and it will intersect at this event. Okay? Now, we have some ways of discussing what this DS will tell you about reality, right? you have three main things. And we've talked about this before. I don't know if the VOD is still up. It probably is not, so let's talk about it again. And if you were around then, you'll have to watch it twice. Well, so yeah, so this is the sand timer, the light cone, right? And like I said, the events happen in the past. Some information will travel to this event, and then this event is, again, in everything moving forward. So let's talk about what these distance lines mean, right? Remember, these are distance lines in Minkowski space. Everything can be described as some distance, right? Where we have all of these things, and we can figure out what it means. So what if the distance squared is greater than 0? Let's start with an easier one. Let's start with what if it's equal to 0. So there's three different cases. There's 0, equal to 0, greater than 0, and less than 0. So let's start with the easy one. What happens if it's equal to 0? Well, then we have the following. Then we have, this just boils down to negative delta t squared, c is equal to 1, plus delta x squared, which is equal to 0. We can take this over to the other side. We'll find out that delta t is equal to delta x by just taking the square root of both sides. And then we can say delta t divided by, let's do this. Let's do delta x divided by delta t, it'll make more sense, is equal to 1. Okay? That's true because I said c is equal to 1. In reality, this should be equal to c, equal to 1. Okay? What does that mean? That is light-like. And where does that exist? Well, we showed you that that exists right here. So now I tell you, I ask you, or I tell you, or I ask you, or I'll ask you. What happens if there's an event right here? Okay? Namely, different color. Namely, B prime. What's the distance between A prime and B prime? Lurk. I'm half kidding. The distance between A prime and B prime when it's on this is what? Well, we already saw. We set it equal to 0. We did a calculation where it was equal to 0. The distance from this point and anything on this point is 0. Why? Because those lines that are on this point are what's called light-like. So, if delta s squared is equal to 0, we call that light-like. Think of like a photon. How much distance does a photon travel if it travels from A to B? 0. Weird. In the reference frame of the photon, it travels 0 difference. That's a very important thing to say. It's in the reference frame of the photon. Okay. What's next? Well, let's take a look at changing one of these. Let's do, what did I do first in my notes? I think I did space-like. Let's do time-like first. What happens if delta s is less than 0? Delta s squared, excuse me, is less than 0. Well, do the same thing, and we get delta t. Delta x is less than delta t. Okay? This is just following the same thing we did last time, where we set delta s is equal to negative delta t squared, plus delta x squared. Delta s squared, excuse me, is equal to that stuff. And then what do we get? Well, again, let's talk about the change in x over the change in t. This is for speed. This is going to be less than 1. But now remember, when you do slopes, what's the slope of a graph? Slope is y equals mx plus b, where m is the slope. M is equal to the change in y over the change in x. Remember all that? Remember that from like algebra? Okay, I'm lost, but I came in late. Yeah, you might be a little lost if you came in late. But we're talking about the distance. This is just a general distance, generic distance in Minkowski space. And we're seeing what happens if things travel that distance, or what happens if we set that distance equal to something. So we say this distance squared is going to be greater than 0, or less than 0, excuse me. So if the distance squared is less than 0, then let's talk about, then we get our slope, delta x over delta t, which is a velocity, is less than 1. Well, what does that mean? Well, remember, like I said, that if you have a change in, so a slope is a change in y over change in x. But here we have it upside down. It's a change in x over a change in y. So in reality, what we should do is figure out what delta xt is over delta x. Delta t over delta x is actually just being greater than 1. Okay? So that's the slope. So now let's draw that slope. What color should we use? I burned all my colors already. Let's do orange. So now, if that slope is greater than 1, then it's going to be greater change in t than in x. So it's going to be like this. What does that mean? This is what you see. This is what happens in reality. This is delta s squared less than 0. Everything that happens in this light cone, information can reach you at A. And then it will go off and reach every event in the future. Right? That's how this works. So say you're talking about some starlight. Some starlight will come in, it'll reach you, and then that starlight will continue to go on into the future. Now, what does that mean? Well, I just told you what it meant. It means that everything that happens within here can hit A. And we just figured that out. So let's look at the last case. What happens when delta x is greater than 0? Oh, so let's write this. Delta s squared is less than 0. We get time-like. Delta s squared is greater than 0. We do the same thing, except now we get delta x over delta t is greater than 1. Or delta t over delta x is less than 1. So that means that our change in x is going to be greater than our change in t. What color should I use? I guess I'll use orange again. So that means we might get something like this, where delta s squared is greater than 0. What does that mean? That means that anything happening in space that follows this trajectory will not be observable. Why won't it be observable? Because you can't measure any change. There's no change measurable because it's outside of the light cone. So it doesn't make any sense to talk about something happening out here, calling it d prime. A prime to d prime. You won't be able to measure that change. It's outside the light cone. So now what we've done is we've taken this formula that is supposed to represent, do you see that? Yeah. We've taken this formula that is supposed to represent Minkowski space, and we've shown how if you have any points inside the light cone, it's described by this, time-like. Any event that happens past here can be observed here, right? Any event that happens outside the light cone will follow the space-like, and you won't be able to observe it because you won't be able to make any measurements. Okay? Lastly, we have a light-like, which happens on the light cone, and you get some sort of infinities and singularities and stuff like that. But this is the basic idea behind what this formula means. Is you have this space where everything can happen. You can talk about a different reference frame. So say you have something moving, you could have another one that looks like this. There could be some object here. We'll call it, what are we going to call it? Alpha. Now alpha's traveling at a different speed. So what's that going to look like? Actually, you know what? I'm not going to draw that because we're going to watch the video to take care of it. and that will take care of that. Okay, so we're not going to worry about that. But yeah, so this is the equation to take care of what happens inside the light cone and what that means if we want to measure distances. All right. Let's see. Slope equal rise over run. Nice. Feel like the Doge. I know algebra, but I still have an idea what Minkowski space is and why everything is zero. I am so gonna rewatch the VOD later, probably several times. That's good at math. Wanted to go on to study physics because it's so free. Oh, that's nothing to be sad about. Software developers are cool too. Okay, I'm okay at math, but I think I'm missing some material here. Yeah, it was the this is, I got stuck at c equals 1. That's not right. I think this is one of the things that stuck with me when I was learning physics, right? And I didn't come to this conclusion until well after I was done learning physics, is that this type of idea about what space is so stinking flexible, and nobody tells you this. Nobody says, like, space is literally just something to talk about. Like, X and Y and Z sound so firm. They sound like everything, you could build everything out of fundamentals. But this is what I was talking about on Stream Monday, right? Is that, what's the difference between classical and quantum? Well, there's this question of whether or not it really even matters, right? Because we have this notion that we need to have everything be predictable. But everything being predictable is so based on what we call space, right? Here, we have something where you have a leg of a triangle that the side length is 0. In Cartesian coordinate space, size 0 means a point. But like, points in reality behave like this. Every space is it's such a general term to wash over everything that it doesn't really mean a single thing, right? What really we should do is say, in each of these different spaces, we can accomplish different things. So if you want to talk about distances, you could talk about, also physically get points for using actual traditional blackboard. You're really effective whiteboards. Thank you. I love that. I love my blackboard too. Hi, Zoiko, how are you? Right, so in special relativity, we start by talking about Minkowski space. In general relativity, we talk about all sorts of different spaces. We talk about what the spaces look like under certain translations. But yeah, so don't get hung up on these different types of spaces, these different types of none of them are more fundamental than the other. They are a prescription for handling a problem. In this particular problem, we're talking about what are we looking at? What are we looking at? Well, we're looking at events. An event happens. The light will travel from that event to me, at which point is another event. And we can talk about the difference in everything with that. We can talk about difference in time, the difference in length. We can talk about what it looks like if you're traveling this fast and I'm traveling this fast. It's just a different way of looking at the problem. So, easy to get caught up in the confusion of what all these different terms mean. But I got lost at cats. It still doesn't say cats. Still never said cats.